For simple harmonic motion, the acceleration is equal to minus omega squared x. So A is equal to minus omega squared x. That is the defining equation for simple harmonic motion. Acceleration is directly proportional to the displacement. Acceleration is directed to the equilibrium position, and the acceleration is always negative to the displacement. So this is in written form. Acceleration is equal to minus angular velocity squared times the displacement. If you were to plot a graph, A is proportional to x, but it is negative. Okay, so I've plotted a straight line with a negative gradient. I'm comparing it with y equals mx plus c. I've put the equation a equals minus omega squared x. Now, comparing with y equals mx plus c, you can tell that the gradient m is the gradient, and you can so you can tell that the m is the gradient, and your m is the gradient, which is y equals minus omega squared. So your gradient m is minus omega squared, right? That is your gradient. Okay, this is the equation for the maximum speed. In this case, v is the speed, right? The speed of the, so imagine you've got something that's oscillating, right? Oscillating like this, oscillating. And this is the speed of the object that is in SHM. Your omega is your angular speed, angular velocity. Your a is your amplitude, and your x is the displacement. Now, imagine you've got a pendulum. It's swinging this way, right? Swinging this way. Now, at this point, it's the fastest. So when it's in the equilibrium position, that is the maximum speed, and this is when x is equal to 0, the equilibrium position, and so v squared is equal to omega squared brackets a squared minus 0. So what you're left with is that the maximum speed v is equal to a omega. Maximum speed is amplitude times angular velocity. This is the equation for displacement. X is equal to a sine omega t. So your x is your displacement. Now, if you're starting with x equals 0, you use sine. And if you start with x equal to a, use cos. Okay, so this is just as a diagram, as a picture. If you're starting with at the equilibrium position, so equilibrium position, this is when x is equal to 0, you use a sine omega t, and if you're starting with x is equal to a, you start with x equals a cos omega t. Circular motion, F is equal to mv squared over r, or mr omega squared. This is for circular motion, and this is the resultant force. This is the force going towards the center of the circle. Okay, so let's use the equations PV equals nRT. So let's look at the question. You've got a meteorological balloon rising up through the atmosphere until it expands to a volume of 10 to the 6 meter cubed, where the pressure is 1000 pascals. The temperature also falls from 17 degrees Celsius to minus 43 Celsius. The pressure of the atmosphere at the Earth's surface is 10 to the 5 pascals. Show that the volume of the balloon at takeoff is about 1.3 times 10 to the 4 meter cubed. So what we have in this situation, you've got a balloon, and then it's rising up, and then it is expanding. So at the start, you've got P1, V1, T1, and then, sorry, that should be 1. And then at the end, you've got P2, V2, T2, right? So let's just write all that down. So your second volume is 10 to the 6. Your second your second pressure is 1000, but your initial temperature is 17, because it went from 17 to minus 43. So your T1 is 17 Celsius, and that is 290 Kelvin. Your final temperature is minus 43 Celsius, and that is 230 degrees Kelvin. So you're using this equation, P1 V1 over T1 equals P2 V2 over T2. Rearrange for V1 because you want to work out the volume at the start. This is when it's at the start, so you want V1 here. Rearranging, you get 1.26 times 10 to the 4, right? And it's just show that question. Next question, calculate the number of moles of gas in the balloon. So here we're using PV equals nRT. Your pressure is this one here, and this volume is the one at the takeoff, right? So this one is this is V1. So this is the volume at the start, V1 at the start, equals N times 8.31 times 290. Remember 290 at the start, 17 Celsius. This gives you an answer of 5.2 times 10 to the 5 moles. And then the mass of the balloon. Now you're given the molar mass. So once you have the number of moles, you times that by 4 times 10 to the minus 3, and then that gives you 2091 kilograms.